Alright, welcome to the first AP Calculus Summer Academy video. Just a heads up, this first one, this first lesson is going to be the longest. In fact, there are two parts. So this is Unit 0.01a, and there will be a Part B. And that's just because there's kind of a lot of stuff from, sort of algebra, stuff that you may have not learned back in the day. That is pretty basic that we want to cover. So before we get into that, I want to talk about how you should organize yourself for this summer with your notes and how to make sure that you get it going into next year. We're in a really good place. So you should have a notebook or a binder with paper that you are going to use for AP Calculus. The reason being is that you're going to want to go back and look at the stuff that you did this summer, because the reason we're doing it is because we're going to kind of be using a lot of these basic skills very often. So what you should do is, in your binder, you should take the first 3 pages and use those as a table of contents. If you don't know what a table of contents is, go ahead and look in pretty much any textbook. It starts out with a section that tells you where everything is and tells you the page number. And that's what you're going to do. Okay, so the first 3 pages just kind of leave blank for a table of contents, and then starting on the 3rd page, you can start with this lesson. Make sure you give it a title, right? So Summer Academy Lesson 1, and for the Summer Academy lessons, write the agenda. Okay, so the things that are going to be covered in this lesson, so that when you're going back and you're looking over your notes, as you build your notebook and have a lot of different things in here, you'll be able to go back to your table of contents where you've listed, you've said, okay, lesson 1, here are the things that it includes, and this is on page 1. Then when lesson 2 comes around, you'll be able to go and here are the things in lesson 2. You make a header, you go back to your table of contents, you can say, okay, here's lesson 2, here's the page it's on. So just to give you a kind of a basic, this is how it will look. Here's your table of contents. Okay, and so your first entry would be Summer Academy Lesson 1, and that's on page 1. Okay, and if you wanted, you could add a few things to tell you what's in it, right? So maybe you add a couple of things: point slope form, x and y intercepts, rational functions, whatever. Okay, and then maybe a couple lines down, or maybe just one line down, you have Summer Academy Lesson 2, and say that begins on page 10. Just kind of making these up. And by the end of the school year, you'll have everything, and you'll be on page 150 or wherever it is. Okay, so let's go ahead and get started. Just a quick note: there will be questions. If you're kind of new to these videos, there will be questions that I'm going to put up and things that I'll say for you to do, and you should do them. You should not just fast forward and wait for me to explain. And the reason is that when you try something first and you get it wrong, but you think about it, or maybe you get it right, that's great. You will find that you're building pathways in your brain where you're remembering things much better. Okay? It's always better to try and fail before you learn something than to just learn it for the first time. Okay? I promise you that is a tried and true, a proven method. And you never know, you might find that you're discovering your own way to do something which will work best for you. Okay, I will say this though, that for some of the questions you may you don't have to copy them down in your notes. I don't think that's absolutely necessary. Of course you can if you want to, but I will say for the questions, it's kind of up to you. The important thing is that you have the notes and the facts and the definitions that we go over. Alright, so when I post a question like this, and it will just kind of pop up, I will let it play for about 5 seconds, so you'll want to press pause so that you don't run into the answers. Answer it, and then press play, and I'll show you the answers. Okay, this should have been review, right? If I know a single point on the line, well, that doesn't actually tell me what the line is going to be. Just because I know that this point, for example, is on the line, doesn't tell me whether my line will look like this, or anything like that.
Also, just knowing the slope of the line doesn't tell me what the line is going to be, right? I could have a bunch of lines that have the same slope, but they're different lines because they pass through different points. However, if I were to know 2 points on the line, well then I know what the line is. Right? There's only one line that can go through those 2 points. And what is really interesting about this is that the reason that 2 points tell us a line is because we now know the slope. Right? If you know 2 points that are on the same line, you can figure out the slope because a line always has the same slope. And so really what we're getting out of this is that we need to know the slope of the line and then one of the points that the line goes through. Okay, so either of these work, but D is a little simpler because when we find 2 points on a line, we still need to articulate what the slope is using those 2 points, and then we can really truly understand what the line is going to look like. Alright, so let's say that we have a line, we know a point on the line, 2, 1, and we know the slope is 2. Okay, so what we want to do is we want to be able to define this line. We want to say, okay, let's write an equation that will allow us to find any other point on the line. So let's just write this point out. Let's just say, it's a general point where we have an x-coordinate and a y-coordinate. Okay, so how can we write an equation that will allow us to figure out, based on maybe the x value that we want to be at, what the y value will be? And what we can do is we can think about this point here, its x and its y value, in relationship to the point that we already know, right? Because we know that the slope is 2. So in order to get to this point here, I'm going to travel some number of x units. Then I'm going to take that number of x units, and for every one of those x units, I'm going to then increase my y value by 2. So in other words, we have 2 things that we're working with, right? We're working with how much did your x value change, and then based on that, we're going to take that and multiply it by the slope to get how much our y value changed. Okay, so just to write this out, what we have is that our change in y, and sometimes you write change as this delta sign, change in y is equal to the slope, I'll put the slope in green here, times the change in x, or delta change in x. And so let's really consider what this means. If I know that my line has a slope of 2 and passes through the point 2, 1, then any other point on the line, I can determine a relationship between the x and y values. Right? So for any other point, the amount that I will have to change the y value by to get to this new point is going to be exactly equal to the number of, the change in the x value times the slope, because the slope is telling me exactly that. What will I increase my y value by for every increase of 1 in the x value? And so now putting these words into actual values, how would you compute the change in y? Well, the change in y is going to be whatever your new y value is, which is this variable y, the output variable. And the change is going to be the new value minus the old value, y minus 1 in this case. And that will be equal to, the change in the y value is equal to the slope times the change in the x value. And the change in the x value is whatever your current, your x value is for your unknown point, minus the x value of your known point, or in this case 2. So you could plug in some values and see what you would get. So let's do one together. Let's say that you wanted to figure out the y value if your x value were 4. Okay, so let's just think about this from a common sense perspective. If your x value is 4, well, that means from your point that you know, you've traveled 2 units in the x direction. And if you travel 2 units in the x direction, you're going to change by 4 units in the y direction. Since this point was 2, 1, changing by 4 units in the y direction will get you to 5, and your point should be 4, 5. And the equation essentially does the exact same thing. We have a relationship here, and we might want to plug in an x value and solve for the y value. So in this case, we're going to plug in an x value of 4, and we're going to say, okay, if we are at a point where the x value is 4, what is my y value going to be? And we can use this relationship to solve for it. So the change in y, or y minus 1, is going to be equal to 2 times the change in x. The change in x, my new x value is 4, so 4 minus 2. And this whole piece here, 4 minus 2 is 2, times 2 is going to be a value of 4. Okay, so I'll just write that here, just save some space. And so we now have that y minus 1 is equal to 4. In other words, the change in y is equal to 4. And since my original y value, the point that I know, had a y value of 1, and the change from that point to my new point is 4, that means my y value is 5. Okay. And so this comes in handy because now we only need to know a point and the slope in order for us to write an equation for a line. Alright, so in general, the equation of a line that passes through a point, x1, y1, with a slope of m is given by y, which is the y value of any other point on the line, minus y1, the y value of the point we know, which is equal to the slope times the x value of this other point on the line, minus the x value we know. And this is just going to give us the change in x from our original point that we know to our new point. We'll multiply it by the slope, and that's going to tell us the change in y, in other words, the difference from the y value of our new point and the y value of the original point. Okay, and so we can write an equation for a line knowing only the slope and point on the line. This looks different from slope-intercept form, but it's really not that different. It's just that in order to write this equation, we don't need to know the y-intercept, which can be helpful. It's not that hard to find, though. And in fact, you could rewrite this equation solving for y, and you get something that looks very similar to slope-intercept form. And here I've done that, and you notice that you now have slope-intercept form. Y is equal to m times x, and this part here is your y-intercept value. And to help you see this, I'm going to rewrite this. So my equation would be y equals mx, and here I'm going to put the y1 first, so I'm going to say plus y1 minus m times x sub 1. And what I'm saying here is that this value here is actually your y-intercept, the value we normally call b in slope-intercept form. And the reason this should make sense is that to find your y-intercept, what you're going to do if you know this point here, you're just going to say, okay, well, we know that this point here is x1 units away from where x is 0. And since our slope is m, we'll multiply that change in x, x1, times m, and we'll subtract it away from what our y value is now. Now if you look at this line here, this has a negative slope, right? So m will be negative, so you'll have a negative times a negative, which is a positive. Whatever your x1 value is, say it's 1 or whatever, that means that you've moved one step to the right of where your y-intercept is, and so you should add 2 to your y value here to get to your y-intercept. And so you'd have a negative times a negative, which is a positive, times the number of x steps that you've taken, and you'll add that to the y value you know to get your y-intercept. Okay? So this would be, of course, slope-intercept form, right? And this is saying here you need the slope and the y-intercept, but that can take a little bit extra time, right? Because you've got to actually compute the y-intercept, and if we only know the point, we know a single point and we know the slope, we'll want to stick with point-slope form. Okay. So you should have a pretty clear idea, right? Two lines that are parallel, they're never going to intersect, right? Two lines that are perpendicular, they are going to intersect at a right angle, right? And so we can think about, in terms of the equation, the characteristics of a line that we know, how might two lines that are parallel be similar? What is the characteristic that they are going to have to share? And then also, thinking about parallel lines, and we use the word normal to talk about lines that are parallel. So this red line is normal to the green line. What would have to be true about this red line in order for it to be perpendicular or normal to the green line? Well, it's pretty clear that looking at the green and the blue line, they have the same slope, right? If they didn't have the same slope, for example, if the blue line were steeper, then it would be pretty clear that the blue line would then intersect the green line. And so they have to have the same slope. So if we're going to have parallel lines, they need to have the same slope. Okay? If we're going to have two lines that are perpendicular, however, the slopes clearly aren't the same. In fact, you can tell the green line has a slope that is positive, while the red line has a slope that is negative. So the slopes are going to be opposites. That's one thing. Okay, but also notice this. The green line appears to be steeper than the red line, and that's for a good reason. So the best way to understand how to determine how shallow your perpendicular line should be is to consider the x and y axes. So the y-axis and the x-axis, those are perpendicular lines, right? And the y-axis is a perfectly straight line, vertical line, which has an undefined slope, right? It is as steep can be. It's so steep that I can't even define how steep it is. And so the x-axis, the line that is perpendicular or normal to it, is going to have literally no steepness, right? It is so flat, it is as flat can be, right? So what we want is that if we have a line that's steep, we need a line that, if we want to create a line that's perpendicular, we need a line that is the same relative shallowness. So if we have a line here that is as a steepness or a slope of 3, then we want to think about how could we take that steepness, right? You can think about 3, it's bigger than a slope of 1, so we might consider it relatively steep. And we want to create another line that is just as shallow as my green line is steep. And so here's how we can think about it. The green line has a slope of 3. Okay, and let's just compare it. How much steeper is a line with a slope of 3 than a line with a slope of 1? Well, it's 3 times steeper. Okay, so how much more shallow do we want our red line to be than a line with slope of 1? We want it to be 3 times more shallow. So how do I make something 3 times as shallow or 3 times less steep? I'll divide by 3, and I will get 1/3. And of course, we also have to remember that we've discovered they're going to be opposite slopes, meaning one will be positive and one will be negative. And so what we're getting at is if we have a line that's steep and we want another line that is the same relative shallowness, we'll take the reciprocal. In other words, so lines that are normal, well, they will have slopes which are opposite reciprocals of one another, whereas lines that are parallel will have the same slope. So now what I'm going to do is I'm going to mark a couple of points on both the red and the blue line, and I want you to go ahead and write the point slope equation for both of the two lines that we just drew. Notice that the points, one of them is on the red line and the other is on the green line, but you want to write the point slope form equations for the red and the blue line. One key thing to note is how I determined the blue equation. Notice that I was told this point on the green line, 1, 2. So let's imagine that we want to pick a point which we know won't be on the green line. Well, we know that since the green line is a line, it will never hit the y value of 2 again. So let's pick
the point on the blue line where the y value is 2, and let's say that the x value is 4. That way we know they don't have this point in common. And so that way when we incorporate that point into our point slope form equation and we give it a slope of 3, we know that the point that we're using isn't on the green line and the slope is the same, so it will be parallel. I could have also thought about, let me come up with a point on the blue line that has the same x value, since the green line will only have one point where the x value is 1, and let me make this point different. So I could have said, this point is 1 comma negative 7. And I could have written a point slope form equation using this point as well.
All right, let's capture these ideas down. So two lines are parallel if they do not intersect at any point, meaning that they have the same slope. And two lines are normal or perpendicular, they mean the same thing, to one another if they have slopes that are opposite reciprocals of one another. So notice there are two components here. They must be opposite and reciprocals. So if I had one line, let's just call it line 1, L1, and for this line my slope M was equal to negative 2, then for line 2, if I want them to be normal or perpendicular, the slope of line 2 must be opposite, meaning it must be positive, and of course I don't have to write it there, but I'm doing it just to show us, and the reciprocal, so positive and a reciprocal of 2 is 1/2. So the slopes would be negative 2 and 1/2.
All right, domain and range. So these are some things that you should be familiar with. The domain of a function are all the input or x values that the function is defined for. The range of a function are all the possible outputs that the function could have. So we'll take a look at an example that should be pretty familiar. This was a pretty easy situation, right? This is a straight line. We can plug in any x value that we want, and we'll be able to get a y value back out. So to calculate the domain, to figure out what the domain is, you just want to think to yourself, are there any x values which if I plugged in, I would not be able to find a corresponding y value? And the answer is no. Any x value you plug in, you'll be able to add 3 to, multiply by 2/3, and get the corresponding y value. Now, another way of writing this is saying that our domain is all x values in an interval. And so we can write our interval, and the interval should go from negative infinity all the way to positive infinity. And that will, tell whoever it is, what's your domain? Well, the domain is all x values that are between negative infinity and positive infinity. And the same thing is true for the range, right? So now that we know the domain, all the possible x values, what are all the possible outputs? And here, sometimes it's helpful to just think of a sketch of the graph. And I'm not going to bother about being super correct about it. I know it's a straight line. So think about all the possible y values that you could have for any point. Well, your line will go on forever and ever. So if you have a y value in mind, your line will be able to reach that y value at some point, and so all real numbers. And again, I can use interval notation, and I can say that the range is between negative infinity and positive infinity. Okay, and that sometimes you'll see people write it as an interval. Of course, as we look at different functions, there will be certain values, thinking about the domain, for example, there will be certain x values where you won't be able to find a solution. Just think about a rational function, right? You don't want to divide by 0, that's undefined, so those will have to be taken out of your domain. Alright, interval notation. So this is something that you've seen in the past, and there's really only two things to cover here. We can talk about an interval with curled brackets and an interval with square brackets. So with curled brackets, if you're saying something is in the interval, curly bracket A comma B curly bracket, what you're saying is that you're looking at the interval, or all the numbers between A and B, not including. Curly brackets means not including. So you'd be considering all of the possible values between A and B, so not including A or B. That's why we have the open circle here. So you might want to just think to yourself, curly brackets means not including. If I'm looking at the interval between A and B square brackets, I am including A and B in my interval. Okay, so that would be all the possible numbers, real numbers between A and B, including A and B. And so often it's just easier to write something using interval notation than to actually write it out with words. Just to give you an example, it's going to be easier for me, for example, to say that the domain is this, than it would be for me to write out that the domain are all real numbers between x equals 1 and x equals 10, including, x equals 1 and x equals 10. That's just too wordy and ridiculous, so I can use interval notation to make my life a lot easier.
Hopefully you like those hints with a little bit of a review for trig functions here. A and B, if you were to look at those intervals, so from 0 includes 0 includes this point here, which is where the function is at 0. That's the value of sine of x when x is 0. And so this is not a positive value, so you can't include 0. And then if you were to continue going on all the way to the 3 pi over 2, once you pass pi and you get into between pi and 3 pi over 2, which is right here, all these values are negative. So sine of x is certainly not positive on this interval. And if I were to plug in x values between 0 and pi, well, that everything would work except for when I plugged in an x value of 0, because sine of 0 is 0, and when I plugged in an x value of pi, because sine of pi is also 0. So I have to exclude those two values there. Let's review a couple of concepts that should be pretty familiar. X-intercepts, these are also known as roots of a function. These are the x values for which the y value is 0. We know that there can be potentially more than one, right? If you have a quadratic function, you might have 2. If you have a cubic function, you might have 3. If you have a sinusoidal function, think about it, you have infinitely many. And then the y-intercept of a function is where the y value when the x value is 0. So in other words, where your curve intersects the y-axis. And you'll notice I didn't put a plural option there. You might think about why it's impossible to have a function with more than one y-intercept. Let's talk really briefly about how we find these values. So if you have some function and you want to find the x-intercepts, well, you're going to be solving for an x value. So what you're going to do is you're going to plug a y value in of 0 and solve for x. So here, to find my x-intercepts, I will set y equal to 0 and solve for x. Very simple. To find the y-intercept, even easier, I will set x equal to 0 and solve for y. Notice the two ways to find the roots of a quadratic. I can factor, and if I can factor, that makes it a lot easier because then I can clearly see what x values will make my y value 0. And if you don't want to factor, you can always solve using the quadratic formula, and you will get the same solutions.
Alright, so here we have a rational function. And we did a lot of things with rational functions this year. And graphing them can be sometimes kind of daunting. A lot of people look at them and get really kind of frustrated and don't know where to begin. But they're actually really simple, and so it's important to just remember that with a rational function, we have a numerator and a denominator. So for example, if you were to evaluate this function when x is 2 or something, you would insert that, compute the numerator, insert 2 here, compute the denominator, and then divide. And that would be your y value, corresponding y value. And so certainly you could go ahead and you could plot a bunch of different points. You could plug in some x values and try and graph this function. But you might find that would kind of take you a while. There's a lot of things you've got to do here, and you might not get be sure what it will look like. So we're going to take advantage of some of the skills that we have worked on over the past couple of minutes in order to make this process much more efficient. So here's what you should do. You should go ahead and find the domain and the roots of this function here. And once you've done that, just kind of see if you can use those to kind of make some markings on your graph that can kind of tell you what your function sort of, it's kind of the boundaries that it has to be within. I don't want to say too much here. So go ahead and find those, and then take a look at your graph and see what things you now know. So the first thing we're going to discuss is the domain. Remember, the domain are all the x values that we could insert, that we could plug into our function that would give us a y value. And this will work for almost any x value, but since we're doing a division, there are some divisors that we can't have, some denominators that we can't have. And what we can't have is we can't have this denominator be 0. And so it might have been helpful to think about what values of x would make the denominator 0. And to do that, if you factored this quadratic, that might make it a little easier. And you could factor it so that your denominator, your numerator is still x plus 1, and your denominator would be x plus 2, x minus 2. If you didn't, that's okay. You can still think about, okay, what would make this 0? And so you could set up an equation, set this equal to 0, or you could just notice that x squared minus 4 will be 0 when x is either 2 or negative 2. So let's go ahead and take a look at the x value 2. Well, we know that there will never be a point with an x value of 2, and so to make that very clear, we can just sort of draw a dashed line for all the possible points with an x value of 2, right? Through the x equals 2 point. And we can do the same for negative 2, right? Because we'll never have a point with an x value of negative 2. And these things here are what we call vertical asymptotes. Okay. Obviously they're vertical, and asymptote is a word that we'll see a good deal more of, and I'll explain a little bit later on kind of what it means. Okay, but for now it just suffices us to know that we'll never have a point that touches either of these lines in our graph, because we can never have an x value of 2 or negative 2. Alright, now let's take a look at the roots. So the roots of a function are the x values for which the y value will be 0. And so we can just go ahead and figure out by solving, setting the y value equal to 0 and solving for x. Right, now there's a couple of different ways that we can do this, and I want to first talk about just kind of in general how we would look at something like this. We want to know what x value will make this fraction equivalent to 0. Well, what I want you to do right now is just write down or think about a fraction which is equal to 0. You would notice, and hopefully you did this, that the numerator is going to be 0, right? And your denominator is going to not be 0. So what you're looking for is any value which makes your numerator 0, just so long as it doesn't make your denominator 0 too. Well, we already know that the things that make our denominator 0 are 2 and negative 2, and clearly neither of those are going to make the numerator 0. So what we really have is just a situation where we are looking for when x plus 1 is equal to 0. And that's going to be, of course, when x is equal to negative 1. Now the other way to think about this is just go ahead and solve it algebraically. If you have a rational expression, you need to get your denominator kind of out of the way. You don't want to be solving for x when x is in your denominator. And so you can multiply both sides by x squared minus 4. And notice that anything times 0 is still 0. And x squared minus 4 over x squared minus 4, that's going to be equivalent to 1, so long as x is never 2 and negative 2. And so we're left with x plus 1. And so our root is at the x value, negative 1. So now we can actually plot this point here. There's our root. Okay. Well, notice that just doing a couple of very basic things, we now have a lot of information about our graph. It may not look like it, but we really do. So in order to clearly illustrate all of the different things we know, I'm going to draw what is commonly referred to as a sign chart. Okay? And so what a sign chart really is just saying, let's look at all of the x values. So let's just kind of redraw our x-axis over here. And on our x-axis, let's just mark all of the kind of important pieces of information. Okay? And so the really important piece of information that we know that there is a vertical asymptote at negative 2. We have a root at negative 1. And we have another vertical asymptote at positive 2. Okay? And we're going to use this little drawing of our x-axis to tell ourselves and really dig deep into what is happening in our graph in each chunk of our x-axis. And there's a reason this is going to work so well. Let's just think about what possibly could our function look like to the left of negative 2. Let me ask you this. Could it be positive and then again at some point negative? Or could it be negative and at a different point positive? The answer is, of course, no. In order for something to go positive to negative, it must cross the x-axis. But that would mean there would be a root to the left of negative 2. And when we solved for the values that will make our y value 0, we did not get an x value to the left of negative 2. The only one we got was at negative 1. And so we know that our function will either be always positive or always negative to the left of negative 2. So how could we figure out which one? Why don't we try out a value? Why don't you plug in negative 3 into your function, do it on a calculator if you need to, and decide whether you're going to have a positive or negative value. If you plugged in negative 3, what you will find is that you end up with a negative value, right? You'll have a negative numerator, and your denominator will be positive. So you know that to the left, and let me label this as what's called a sign chart. And we'll make lots of these. They'll become very, very helpful. To the left of negative 2, our function is always going to be negative. Okay? So we know it's always going to be negative. And now what we want to do is, since we know it's always going to be negative, we want to decide what's going to happen as it moves really far to the left. And then what's going to happen as I move really close to negative 2. Okay? This is what's called the end behavior. So think about what happens as your function, you plug in x values that are very, 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 very negative, like negative 10 million. Okay? Well, why don't you try plugging something very negative into your function? For example, if you plugged in negative 100, you would have a negative 100 squared, which is a very big positive number, minus a small number, so you have a very big denominator. And then your numerator is going to be negative 100. So if you type that in your calculator, you'll find that's very close to 0. It's a very small negative number. So in fact, the further you go, and you could try more and more negative numbers, you're going to get closer and closer and closer to 0. This is what's called the end behavior. Okay, so we know that as we are moving to the left, further and further, we're going to get closer and closer and closer to 0. Okay? And this is also what's called a horizontal asymptote. And the word asymptote, I'm going to say a little bit more about it now. An asymptote is something which you will get very, very close to, but never actually touch. Okay? So we'll get very, very close to an x value of negative 2, but we'll never actually touch it. We'll get very, very close to a y value of 0 as we move to the left, but we'll never actually touch it. Okay? All right, then we need to decide what's going to happen as we get very close to negative 2. Well, you could plug in a number that's just to the left of negative 2. For example, maybe negative 2.1. Well, go ahead and try that out. If you plugged in negative 2.1, you're going to get a very, 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 very big negative number, right? And so that means you're going to be way down here. And if you plugged in even a number even closer to negative 2, you're going to get even more negative. So we find that as we move closer to negative 2, our function is going to approach negative infinity. And we can just kind of connect. And there we have our function to the left of negative 2. All right, what I want you to do is go ahead and try this same idea for what the graph will look like to the right of positive 2. All right, so if you are working with numbers to the right of positive 2, say you plugged in positive 3, for example, you will end up with a positive value. So you know that to the right of positive 2, your function is always going to be positive. And then we can kind of go through this same process we did before. What's going to happen to my function as I get bigger and bigger x values, as x approaches really, really large numbers? And what's going to happen as my x value gets closer and closer to positive 2, right? Because those are the extreme values that we can get to. We can get really close to 2. We can't actually get to 2. And then we can also go all the way out to positive infinity. And we know that it's never going to go negative. Okay? So if we were to plug in some very, very large positive values, like maybe you plugged in 100 and then 1,000 and then 1,000,000, right? You are going to see that our denominator is going to get very, very big, but the numerator is going to be relatively small, right? And that's because I have this squared term down here. And so as our function, the x values get bigger and bigger and bigger, move further to the right, our function is going to get closer and closer and closer to 0. Remember, we know it's never going to hit 0, right? It's never going to hit the x-axis. It's never going to go negative. So I am very confident that no matter how far I go out, I'm always going to have a positive value. It's just going to get very close to 0. And so that is a horizontal asymptote. So I'll go ahead and label these here. I'll just put an H for horizontal asymptote. And what an asymptote is it's a value that your function will get very, very close to, but never actually touch. So the vertical asymptotes are x values that you'll never actually touch, and horizontal asymptotes are y values that you will never actually touch as you move far out to the left and far out to the right. Okay, but the horizontal asymptotes, important to note, these deal with what's called end behavior. Okay, so I might also say, I call this end behavior. Okay, And what end behavior is what your function is doing towards the ends of your x-axis, towards the values that are close to negative infinity and the values that are close to positive infinity. Okay, so now we know what's happening as I move further and further to right. What happens as I move further and further to the left up towards positive 2? So you could try some values like 2.1, 2.001, 2.0001, and you'll find that your denominator now is going to be very, very, very small, and your numerator is going to be relatively much bigger. And so you're going to get very big positive values. And so we can move up like that. And so now you have the right side of your graph plotted. And the only thing left is for us to decide what's going on in here. Okay? Well, let's think about the possibilities. Okay? And this is where the sign chart really helps. We need to figure out what our function is going to do between negative 2 and negative 1. Okay? Because we know it's either going to be positive or it's going to be negative. It can't be both because the only root we have is at negative 1, and so it will be impossible for us to cross the x-axis before we get to negative 1. So let's plug in some value to find out whether it's positive or negative. And if you do so, you're going to find that it is positive. And so now we just need to decide, okay, what's happening as I get closer and closer to negative 2? Am I going to be, what's going to happen? And so you could plug in some values that are very close to negative 2, maybe negative 2.01, so on and so forth. And you'll find, not surprisingly, that since it's positive and you're getting closer and closer to this asymptote, you're going to get closer and closer to positive infinity. And then you know that as you move towards negative 1, it's got to get closer and closer to negative 1 because you've got to hit negative 1. You know it intersects at negative 1. And so now at this point, you're almost done. You only have one other section of your graph to figure out, and that is the section between negative 1 and positive 2. And think about your options. It can either be positive again, meaning it will hit your root and then come back up and be positive, or it could continue down negative, and as you get closer and closer to positive 2, you could get more and more negative. Okay? So plug in some values and see what you get. Alright, well the easiest one would probably be to just plug in 0, and 1 over negative 4 is negative, so you know that in between negative 1 and positive 2, your function is going to be negative always. And by this point, you should be noticing that as you're approaching your asymptotes, your function is getting closer and closer to either positive infinity or negative infinity, depending on the sign of your function. Okay, and that'll be something that you'll see as you try this over and over again, right? As we get very, very close to our vertical asymptotes, that means that our denominator is getting very close to 0. And when we have a denominator that's very, very small, our value is going to be very, very large, either very large positive or very large negative. So I know that I will come down, try and make this as smooth as possible, and approach negative infinity. Alright, so that was a lot, and that might seem like this is going to take forever and ever, but I really went through the nitty-gritty of the details that are actually, when you're practicing them over and over again, are going to come very, very quickly. So what we've learned here is that using the domain and the roots, we can find what's called critical points. Okay, these are the points that I'm plotting to start off with that really help me understand what my graph is doing. And then once I make this sign chart with the vertical asymptotes and my my roots, and I may have more than one, I can just figure out what the sign is going to be in each of these intervals, right? So this is the interval from negative infinity to negative 2, and from negative 2 to negative 1, and from negative 1 to positive 2, and from positive 2 to positive infinity. And then based on that, I can look at the end behavior and know what's going to happen as I get closer and closer to the vertical asymptotes and sketch a graph of this function. Alright, lot that you went over here. I'm going to give you one example to try on your own. Give it a good shot. Give yourself a little bit of rest, and then go ahead and tackle the next video.